Story of these materials, and what I want to stress is that it started with curiosity, and then following curiosity, it became a real technology which has impact all over the world today. Uh, so let me tell you first a little bit about myself. I was born in Paris, and my father, Moungi Bawendi, was a young mathematician, and we went back and forth between Paris and Tunis. You know, many times as I was a child, grew up in Tunis, not far from here, for a number of years. Then we went to Nice, back in France. Then we went to the US. Well, here I am as a child, right here. It's my father. One of our many trips back and forth between Paris and Tunis. And then in 1971, my parents emigrated to the United States. And this is me in the airport at Orly, thinking that I was just going to go somewhere where, you know, just like going from Paris to Tunis. And my mother had told me, you know, that in the US, people don't speak French. And I didn't believe her. So I didn't know any English. And then I came to, you know, the middle of the United States, West Lafayette, Indiana here. There's a university there, it's called Purdue University. On remplace une lettre, le petit U, ça devient perdu. And I was very lost. J'étais complètement perdu, hein, complètement. La première fois, j'étais dans la rue et il y avait un petit garçon qui est venu pour jouer avec moi. Il m'a dit hi. J'avais aucune idée ce qu'il disait. So I learned English very quickly. Yeah, 6 months later, I was fluent in English. And then we went back, you know, back to Paris for high school, you know, back and forth, and eventually, you know, I came to Cambridge for Harvard University, and then at MIT now. I've been there since 1990, so I've lived almost all my life in Cambridge. Okay, so I went to college, like you were at college, at Harvard, and my first year, the first exam I took in chemistry, je vais tout casser ici. My first exam in chemistry, I had a habit of getting lost, you know, lost as a child. I was lost, and the first exam, I got the lowest note in the class. It was 20 out of 100. And I thought that was the end. I thought that was the end of me going to university. And I was going to go back home and never come back. But I learned what my mistake was. You know, I learned that I didn't know how to study. I didn't know how to study. I didn't know how to study for an exam. And I learned how to study for an exam. And after that, I didn't have any more problems. But studying for an exam and doing research are completely different things. You know, it's a different part of the brain. And so you have to learn both things, right? Because it's also important. They're both things that are important. So then after that, I became interested in research. And I went to the University of Chicago for my PhD, Laureat. And I was very interested in physics, but chemistry also. And so that's where I started doing experiments on very, very small molecules. The smallest polyatomic molecule you can think of. Polyatomic means more than 2. So this is three nuclei. It's H3 plus. 3 protons, 2 electrons. You can't get any smaller than that for polyatomic the experiments I did were very fundamental, quantum mechanical experiments, looking at the spectrum of the vibrations of this molecule. And I loved it. I loved it. And the claim to fame of my research was that in the 1990s, there was a comet that exploded in the solar system. It exploded in 3 big chunks. And those 3 chunks collided with Jupiter, the planet Jupiter. And Jupiter is made up of hydrogen. It's full of hydrogen. And the explosions created enormous energy and created a large amount of H3 plus of this very small molecule. And my research as a graduate student was used to calculate the energy impact of that collision with Jupiter. It's enormous, huge, huge energy. But I felt like my research, my fundamental research, was actually useful for something. It's not a technology, but it was useful to understand something interesting about our solar system. Then, after a few years at Chicago, I had the opportunity to spend a summer at Bell Laboratories. Bell Laboratories was an amazing place. It was created in the 1940s. It was part of a company called AT&T, which was, in the United States, was the phone company. And it had a monopoly. It was the only phone company. And it made a lot of money because it was a phone company. And with all that money, it funded this research laboratory, Bell Laboratories. And it was amazing because it was a place where you had these amazing scientists that had a lot of money to buy equipment. A lot of money to buy equipment, and they were given a lot of freedom to think, to do experiments, and not very much supervision. There was not a lot of bureaucracy. You wanted to do something, you wrote a couple sentences, and you gave it to your department head, the people in charge, and you said, I want to work on this. They would look at it and say, oh, that sounds interesting, and they would give you a lot of money to do it. This place doesn't exist anymore, because AT&T is no longer a monopoly. There's not that much money with AT&T. But this is where the transistor was invented, this is where photovoltaics were invented, this is where the fiber optics were invented. All these inventions that we live with today were invented at Bell Laboratories. So when I went there, it was still an amazing place. And I worked with Louis Bruce, and I discovered this world of physics that I didn't know much about, and some of the chemistry that I didn't know much about. I was fascinated. This is where I learned about quantum dots for the first time. And so after graduating, after my PhD, I came back to Bell Laboratories for a postdoc for a couple of years. And after that, I went to MIT in 1990, and I've been there ever since, my home. I love MIT, it's an amazing place. It reminds me of Bell Laboratories, having scientists and engineers from all disciplines working together. It's very easy to talk to each other. It's essentially all connected. One big building, and then there's some buildings, but it's easy to walk. For instance, my office, when I first started, next to me was the astronomy department. Then further down was the computer science, and the condensed matter physics, and the particle physicists, and then the chemists. So we're all together, and it's very easy to talk to each other. The students can really talk to each other. And also there is a lot of entrepreneurship. There's a business school. There's a lot of startups that come out from the engineers. So it's really an amazing environment. And that's why I haven't left. Okay, so now let's go back to the subject of this meeting, of my talk, which is, what is a quantum dot? So a quantum dot is this little particle We used to call them little particles. Now we call them quantum dots. It's nanometers in size, which means it's got a few hundred atoms, maybe 1,000 atoms. This is a binary semiconductors. It contains two elements. When you think of semiconductors, you might think of silicon. Silicon only has one element, but there are many different kinds of semiconductors. Right? The one that we used for most of our research was cadmium and selenium, cadmium selenide. That's the semiconductor. It's a crystal, but it has these properties of the semiconductor. So it's very small, and it shows, when you put an electron in there, it shows what we call quantum size effects. And I'm going to explain this to you. So they're very small, and so sometimes you need a new technology to be able to advance science. And the technology that allowed nanoscience to really advance was electron microscopy. Without electron microscopy, we wouldn't know what we're doing. So electron microscopy allows us to see really tiny things. It's an amazing technology. So here's one of my students with the electron microscope. This is an old electron microscope that we had at MIT at the time. Today they don't look like that. Today the electron microscopes are just big boxes. And everything is computerized and automated. There are no knobs. But I like knobs. I like to turn things. So when you use the electron microscope, then you see down to sub-nanometers, many angstroms. And so that's what they look like when you have a sample of these particles that are almost all the same. You've made a good sample. So without this technology, without the electron microscope, we wouldn't have been able to do what we did. Right? So who knows what new technology today is being invented that will allow science, to proceed. Okay, now let me tell you about the quantum part, the magic of quantum mechanics. I love quantum mechanics. I think it's incredible, the properties of quantum. So one of the properties of quantum mechanics is this idea of particle-wave duality. That an object, like an electron, can be both a particle, but also a wave. That's fundamental to quantum mechanics. And the property depends on how you look at it, but they're both there at the same time. And this property is super important, it's fundamental to the idea of the quantum dots. So I want to convince you that electrons have the properties of waves. This is an experiment that was done in 1989, so not that long ago, given that quantum mechanics is 100 years old. So in this experiment, so this is inside an electron microscope, the big thing that we just saw, the picture of, right? So this is inside this microscope there, right? Inside the microscope. And inside that microscope, there's a source of electrons. And that source of electrons brings out one electron at a time in this experiment. So one electron comes out, you wait, another electron comes out, you wait, another electron comes out. Then there is a little filament here, a very tiny filament, about the width of a hair. Small, but still it's not nanoscale, right? It's macro scale, it's human scale. And then a couple plates, and these are all positively charged, so they repel the electron. So this one electron comes out, and it has a choice of two paths, right? They're identical paths. Then it comes and hits a scintillator plate, a camera, basically, and you see the electrons appear out here, right? And so if you think of electrons as particles, you think, okay, so that electron comes out from the source, and it picks a path, and then we see it sort of randomly on the plate. And what the image that we see here, we think classical like particles, maybe we'll see a shadow of that filament, and we see a big amount of electrons here, big amount of electrons here, and then the shadow between. Okay? That's what we think of, particles. This is the classical thing. That's not what quantum is. So let's do the experiment. let's see what happens. Okay, so there's the, okay, so the video is supposed to start. There we go. So these are the electrons, one at a time, hitting the scintillator, the detector there, right? So you say, okay, so that electron there, maybe it chose the right path, the left path. Then we see it as a particle hitting the detector, right? And it's kind of random, and you don't know what's going to happen. And you know maybe there's going to be the shadow in the middle, and then you have a lot of electrons here, a lot of electrons there. We're going to speed up the experiment, because otherwise we spend 20 minutes just staring at dots on the screen, right? We don't want to do that. So, speed up the experiment, and what's happening here, still very random, completely random, and then very slowly you see a pattern appear. Right? You see a pattern. And the pattern is that there's no shadow in the middle, there's no big blob, there's a series of stripes. Right? A series of stripes. Why are there stripes? These are because these are not particles. These are waves. So this is like a different kind of experiment. I don't know where to point this thing to go forward. Here we go. So it's like waves. So if you think of the electrons as waves, as one electron is one wave, it has two paths, like water waves, like in the ocean, right? There are two paths. There's two little holes here where they can come out. The two little holes are like the two different paths. And the wave comes through both holes at the same time, right? It hits both holes, and you have these little waves, little circular waves coming out, and they interfere with each other. And then you create a series of high and low probabilities here. And so this pattern is exactly the pattern that you see here. So that means that electron up here, that one electron, it doesn't choose one path or the other. It sees the entire apparatus at the same time. It sees both paths. It doesn't choose one or the other, it sees both, and it interferes with itself. And the idea of a particle interfering with itself, right, blows your mind. Right? How can it go through both paths at the same time? It's because it's a wave. And that's the incredible thing about quantum mechanics. It's these ideas, these things that we can't really think of very well. But the idea of the electron as a wave is super important for quantum dots. Okay? So how is it important? Okay, so we already talked about the electron as a particle. It carries charge, energy, etc. But if you take that particle and you put it in a tiny box, okay? Now it's like a wave. It's like that electron seeing both paths. It's the property of a wave. It doesn't go around the box really fast, It doesn't move around the box really fast. It just sits there as a wave. It just sits there. The whole box, it sees the entire box at the same time. The entire box doesn't move around. It's just a spray sitting there. And so when we accept that, when we accept that it's just there as a wave, then all these properties become obvious. Okay? The properties of waves in cavities. So we're used to properties of waves in cavities, for instance, for sound waves. For instance, we know that, so our box is, the nanobox is the quantum dots, and we call that quantum confinement. We're confining the electron in the nanobox. Okay, now if we accept the wave and the cavity idea, if you have a sound wave, you know that a flute has a deeper sound than a piccolo, right? The pitch is higher here because it depends on the size of the cavity. The same thing for organ pipes. These little tiny organ pipes have a higher pitch than the big organ pipes. Here we go. And put this in color. Right? High pitched, I put in blue. Low pitch, I put in red. Middle pitch, I put in green or yellow. Because it's the same thing with light. Light is a wave, right? We don't call pitch for light, we call it color. Color. Small wavelength light is blue, long wavelength light is red. It's like pitch for sound. Okay, so cavities and waves are super important. And same thing, so these are like cavities for electrons. Right, so, but how do we put an electron in there? These cavities are already full of electrons. They're full of atoms. Atoms have many electrons. Cadmium has 212 electrons. A lot of electrons, but they're all connected right next to their nuclei. They're all bound next to their nuclei. So we have to put an electron in there, confine that electron, put it in the box. How do we do that? We have to add energy. We add energy by taking some blue light, a photon, particle of light, and we strike the quantum dots with that energy, and we liberate one electron from one of these atoms to occupy the box. Right? So, keeping the analogy with waves, when you play guitar, you play the violin or something, you have strings. When you pluck the guitar or the lute or whatever, the string vibrates. Okay, that's the wave. Striking it is the energy. So the photon is like striking the string. You create the sound wave. So now that electron, eventually, that electron is going to find where it came from. It came next to an atom. It was liberated, the entire box. Eventually, it finds where it came from, goes back to the atom, and in that process, it releases its energy. Energy came from the photon, you create the wave, then it releases energy, it releases it as light. And this is why we see these things glow, different colors. It's that cavity, the wave, the electron inside the cavity, you see different colors, just like you see different pitches for the organ, for instance. Okay, so that's the basic idea of quantum dot. So now, this idea was thought of many, many years ago. It was thought of, I want to say, 1950s, even earlier, because it's a very simple idea. Very simple quantum mechanical idea. It's a problem that we give to physics students. It's called the particle in the box. It's very simple mathematically. It's beautiful mathematics. But in order to realize that idea in a real system, in a material, we have to work, right? We have to do something. So the first two people to realize this idea were Alexei Ekimov and Louis Bruce. And they were the discoverers of the material for the Nobel Prize. They were the discovery part. And I worked with Louis. He was my postdoctoral advisor. So Alexei was working in the Soviet Union. He was working in St. Petersburg. It was called Leningrad. He was in Leningrad back then. The 1970s, or 1980s, he was a physicist. He is a physicist, he's still alive. And what he was interested in was understanding the colors in stained glass, like in churches, cathedrals, or other stained glasses. And it was already known that the red color is made up of nanoparticles, tiny particles of gold. When you make gold very, very small, it doesn't look yellow, it looks red. And Faraday knew that already in the late 18th century. He was able to make little particles of gold, and some of his solutions of gold particles still exist in Cambridge, in the United Kingdom. You can see them in the museum, Cambridge Museum. But what about the other colors? The green and the different shades of red, and the yellow, etc. So that's what he was interested in. That was the curiosity. right? So this is the beginning is all curiosity. Right? You're asking why, why and how, and curiosity. How did these colors form? And so he was able to take glass, molten glass, with just a couple elements in it, and realize that by processing it, by heating it up and cooling it in different ways, he was able to make different colors from the same material. Kept copper chloride first, and kept sulfide, semiconductors, and every time he got a different color. He used small angle X-ray to be able to measure the size of the particles, and he was able to correlate size and color, and he was able to understand it, and he wrote a paper in 1981 with the first three words, quantum size effect. The effect that I showed you. Yeah? You take the wave, the electron wave, you can find it, it's quantum size effect. And he wrote it in Russian. And it took 3 years to be translated into English or so. At the same time, Lewis, working at Bell Laboratories, he had no idea that Alexei existed, because this was the Cold War, right? It was an iron curtain between the Soviet Union and the United States. There was no communication between the two countries. So he was working at Bell Laboratories, and he was interested in understanding how fast an electron goes from inside a semiconductor to a solution to do photochemistry. Because he wanted to understand, it was a time of an energy crisis, the late 1970s. OPEC had put an embargo on oil, and scientists were trying to understand how to make fuel from sunlight, how to do renewable energies, something we're still interested in today. And you could use semiconductors for that. You take sunlight, you put that energy into a semiconductor, you create electrons, you try to use electrons to do chemistry to create fuel. And the fundamental process is that electron has to go from inside the semiconductor to the liquid. And there was a new technology invented that allowed people to study that. It was called the picosecond laser. It was a laser with a very short pulse that allowed you to time the process down to picoseconds, 10 to the minus 12 seconds. So he was using that new technology to try to understand this, and he was using sulfide, and every time he made a sample, it looked different. He made the samples with the particles smaller and smaller because it's a surface process, and he wanted his surface to volume ratio to be as large as possible to get a large signal in his experiments. And so he made the particles smaller and smaller, and then every time he did the experiment of making the particles, he got a different color. And he thought maybe he wasn't being a good experimentalist, maybe he was making mistakes, but he was at Bell Labs, and he had electron microscopes. He had a lot of money, so they had electron microscopes, and he was able to see that the color correlated with the size. And he wrote a paper in 1983 with the first three words, quantum size effect, the same three words as Alexei, right? They didn't know each other. No idea they were working on the same thing. And a lot of more words here, redox potential, that's because he was interested in photochemistry. And it wasn't until many years later, that Lewis found Alexei's paper, wrote him a letter, said, we're working on the same thing, we should talk. But the letter didn't go directly to Alexei, it took a little detour to the KGB. And then Alexei got a visit from the KGB agents asking, what are you working on that's so interesting? Why is it so interesting that this guy in the US wants to talk to you? Yeah. So where do I come in? I come in because the chemistry that Lewis was doing was based in water. You take salt, hydrogen sulfide, react together at room temperature, actually even lower than room temperature in water, and we see these things. But it turns out that water is a terrible solvent for semiconductors. There's all this oxygen around. And if you take a lot of surface, and sulfide, put it in front of oxygen, it oxidizes, it becomes cadmium oxide very quickly. And room temperature is not a great way to make crystals. If you want to make these kinds of crystals, you want to go to high temperature. That's very crystalline. And so that's what we realized at MIT. And this is the paper that was already cited, the 1993 paper with my three students. So let me tell you about the process that we invented. So I had realized, working at Bell Lab before going to MIT, that in order to make particles that are essentially all the same size, they're very simple ideas. Very simple. It was the hard part was to make the simple ideas into reality. And that's always the hard part. So the simple idea is we needed to separate the nucleation and the growth. We needed to make tiny seeds first, and then slowly grow these tiny seeds. But to do it at the nanoscale, adding a few atoms at a time as the thing goes. And we had to do it at high temperature to do high crystallinity, and we didn't want any water because that was very oxidizing. So we had to get rid of water and oxygen, high temperature, nucleation growth. And I was not a chemist. I was really more like a physicist than a chemist. So whatever whatever we needed to do, it had to be simple. Because I wasn't going to synthesize a complicated molecule. I didn't know how to do that. But the idea was simple. And so my first students, Chris Murray and David Norris, they're both professors now at Penn in the US, and at ETH Zurich. So we came up with this simple idea of taking molecules that contain the elements that we want as metal organic precursors. This is inorganic chemistry. And we inject the metal, they're stable at room temperatures, they just sit there at room temperature. But when you put them at high temperature, at 300 degrees Celsius or even higher, they decompose and they release the elements, and the elements have become very reactive. And that's the seeds. We decompose it very quickly, we inject really fast, we create the little seeds. We have ligands. Ligands are molecules that attach to the surface, right? And they slow down the growth so that the growth becomes slow and steady. So we have injection, creating of little seeds, and then a slow growth at high temperature. Because at high temperature, we can lower the temperature at any time to stop the reaction. And we have different sized particles. So the idea is pretty simple, right? But it took a lot of work to actually make it go. And the students are all so important because I'm sitting in my office and I tell my students what to do. And a secret of being a good professor is to find students that are smarter than you. It's true, huh? It's true. Because then they can do the things that we just read about. So he's smarter than me, and he's smarter than me. Okay, so this is what it looks like, right? There's the syringe with the metal organic precursors stable at room temperature. And then this is at 300 Celsius. Quick injection. These are the seeds. These are nanometer size, and they need 100 atoms. And they're now slowly going to grow. Right? The color is going to change. And so now they're going to wait. We're not going to, again, 20 minutes, we're going to cut it. There's 20 minutes later, and now it's a different color, much deeper red. It's like the organ pipe getting bigger and bigger, right? And then you see the different, you take samples out, and you see the different colors coming out, the growth of these little tiny nanoparticles. So this experiment, this paper, as was said, it was very important because it was the beginning of understanding how to manipulate materials at the nanometer scale. Right? How to manipulate material in this very strange world of nanomaterials. It showed that you could do it, and that You could create new properties. And then you can engineer the properties. You can engineer material at this size scale, very precisely. So we wrote a paper, this paper, and there's a few words in the abstract that turned out to be really important, that we didn't know it at the time. Okay? Because we had no idea what it was good for. All we wanted to do was understand how the properties changed from tiny particles to bigger particles. How did it evolve? You know, that was the curiosity of how does it change? Why, how does the cavity make things different? But in that abstract, we explained that it was simple, it was a single reaction, and then we had a way to purify. This is a way to purify the material. Whenever if you're a chemist, you make a new molecule, you want to isolate it, you want to purify it, you want to make it pure. This was a way to purify it. Okay. Simple and single reaction as a technology, for making it a commercial technology, was really important, it turned out. Because if you look at a material or a molecule, the cost depends on the number of steps it takes. You have a drug, a pharmaceutical material. The more complicated the drug is, the more expensive it is to make. You have a semiconductor chip. The more complicated the chip is, the more expensive it is. The more steps you need, every step adds an expense. If it's a simple, single reaction, it's going to be cheap. That turned out to be really important. One step. Right? So today, this idea, this process is being used in huge reactors, 500-liter reactors, 1,000-liter reactors. It's the basic idea still. And so these quantum dots are produced at very large scales in Japan, Korea, China, and then they're used almost all of the space. Okay, so that was that changed the field. This is why the Nobel Prize is here. There was another important innovation that happened a few years later. So I want to also talk about the time it takes, right? The time is important. So the discovery, the idea of the thing was in the 1940s, didn't become a material until 1980, right? 40 years later. Between 1980 and 1993, it was just a curiosity. This is a process. Who knows what it's good for? It wasn't good enough to actually study physics. It was not, the properties were not good enough. So 1993 was when we created the synthesis. And then in 1996, the idea to protect the quantum dot with other semiconductors to encapsulate, to increase the efficiency of the light coming out was important. It was not a new idea either, but it was the way of doing it. And so that allowed then the emission, the light coming out from the quantum dot to go up from the efficiency to go up from about 20% to about 100%. That turned out to be important in the applications, right? For understanding of physics. And it was another, so science is a series of inventions. Nothing is, it's a path. And along the path, there are a bunch of important inventions. There was a really important invention in the 1990s. It was the blue diode, gallium nitride diode, source of blue light, solid state blue light. That was invented by Nakamura, working in Chiba in Japan. He was working all by himself. He invented the blue diode, which has changed the world. It changed lighting. We have LED lights, we have LED televisions, amazing technology. But it was a source of blue light, very cheap, efficient source of blue light. At 460 nanometers, right here. And the quantum dots This is the absorption of quantum dots. It's like a semiconductor, so it absorbs blue light very efficiently. They all absorb blue light very efficiently. They emit light in a very narrow range. So all these dots here are all being excited to the same wavelength. And organic molecules, even though they have beautiful colors of fluorescence, you need different colors to excite them. Blue light doesn't work for all of them. It only works for certain. So the dots, combined with this invention, that was the key to the commercialization of the technology. Now remember, in the 1990s, we were starting to get samples of these blue diodes. I got some samples from Julia Packard. I was in the lab, trying to put polymers and dots together to show that you can take some blue light and make it into different colors. So I actually went to the lab and worked on it myself. Okay, so this then. So the first application that we thought of, because we were chemists, you don't think too far away from your field. Right? You're constrained by your field. And as chemists, the closest thing we had was biology. Biology is big molecules, biomolecules. So we knew about fluorophores, organic molecules that emit light to tag cells. Companies were selling these things. We thought, wow, quantum dots, we can use the same blue light, we can then multiplex. We can have all different colors, we can have different sized dots attached to different parts of the cell. We could image the whole thing at once. So that was the beginning of the first company, Quantum Dot Corporation, which I helped to start in 1998 with Paul Savas from Berkeley. Now it's part of Thermo Fisher, a huge company. So that company that developed quantum dots for biology, and this is a paper from the company showing these are dots in the nucleus of the cell. These are dye molecules in the skeleton of the cell. And one property of the dots is that they're very stable to life. They don't fade away. The organic molecules, they fade away because organic molecules are made up of carbon-carbon bonds. You break a carbon-carbon bond, the molecule no longer behave properly. But quantum dots are these three-dimensional solids. You break one bond, the atoms have nowhere to go. They're right there, right? So they don't fade away. They're very stable, which is